Okay, so one of the clearest applications for moment of inertia in the parallel axis theorem is when we look at composites, because obviously in the composite case, just like for the centroids, we will calculate it, right? But that not every shape shares the same centroidal axis location. So the centroid, of course, for the triangle is way up here, for this rectangle, and the rectangle is somewhere else, right? But there's probably some global, right, uh, um, axis, right, that represents the centroid of everything. So similarly for the moment of inertia, we will also use the parallel axis theorem and the same idea of the composite areas in the sense that we can subtract them from each other, right? So we'll take the triangle as area 1, the rectangle on the outside is area 2, and the rectangle on the inside is area 3. And so if we're asked to calculate the moment of inertia with respect to the x-axis, notice that the x-axis is way down here at the bottom. And so this is when it becomes particularly important when you're looking at the tables to make sure that you're paying attention to which axis is used in the table to draw everything or for your calculations. So for this example, we'd have the moment of inertia would be equal to Ix1, whatever that is, plus Ix2, the rectangle on the outside, and then we'll subtract the moment of inertia from the empty space. Right, so one way we can think about this, right, let me draw these individually. So we have the triangle, right, um, way up here. We have a rectangle that's on the x-axis, and then we have the empty space that's floating above the x-axis by some amount. And so this, right, would be d1 for Ix1. This one is d2, right? So all of them will require the parallel axis theorem because the centroids of each of these shapes do not lie on the same x-axis, right, as the x-axis that's given in the problem here. So the fact that this centroid of the triangle is some distance away, this one for the big rectangle, for the little rectangle, right, is going to basically be our centroidal axes, right, are here. So this is like your x1 prime. This we could say is our x2 prime right here. And then this one would be x3 prime. And then you just have to calculate where those are and just pay attention, right? So to the details of these problems. So for example, for D1, we know we're going to have to go up the 400, up another 50, and then up a third of the way, right? So a third of 240 is 80, right? So this distance here, from here to here, is 450, right? And then you know we're going to need to be another 80 for that. So that's 530. And then D2 is just halfway up, right? That's going to be the 225, right? Halfway this distance, right? So we could kind of make a table just like we did before, right? And so I'll just write the example for one, and then we'll keep going through the rest of them. So we have Ix1, for example, is equal to the moment of inertia with respect to the centroidal axis, and now accounting for the fact that we have to use the parallel axis theorem, which would be the d1 squared. So let's go ahead and just make our table. So we know we're going to need to do that for all three of these, right? So we have area 1, area 2, and area 3. And I know I'm going to need an Ix, right, value, an area value, and our D value for each of these. So we have a 1, 2, and a 3. So the moment of inertia, we can actually go calculate it or look it up in a table. And so what you'll be given, right, are tables like this that have what the moment of inertia is for different shapes. So for example, for a triangle, the moment of inertia depends if it's with respect to the centroidal axis or, right, with the axis at the bottom. So for us, we're calculating Ix prime in this example. So that's where we're going to get 1 over 36. I know it's probably hard to see on the video, but 1 over 36 times bh cubed. We'll also need the the moment of inertia with respect to the centroid for the rectangles, which is our 112 bh cubed, right? And again, just pay attention that it's base times the height and not to flip the h and the b's, right? But if you accidentally pick this one out, right, then you would have the wrong one. This is actually the one that it counts for the parallel axis theorem, like in the previous example. So we are getting the prime ones, right? The centroidal moment of inertias. So when I put these in, I'm going to have 1 over 36. So sorry, I squished this up. Times the base, let's say, the base of the rectangle time, or the triangle. So B1 H1 cubed. And so here B1 will be equal to the base of the triangle, which is the 300. H1 will be equal to the height of the triangle, and that's all based on the table below, right? And then of course the area, 1/2 base times height, 1/2 base times height. And then our d value is from up above, 530. Again, the distance from the axis of interest to the centroidal axis. So now for rectangles, we know that our general formula is going to be 1/12 times the base of the rectangle. So we'll call this one B2 times H2 cubed. So here B2 would be, again, 300. H2, the height of this one is 450. Area, of course, is an easy one, B2H2. And now again, our centroidal distance, right, is the distance to the middle of that rectangle. Rectangle's 450 millimeters high, so we know we'll go halfway up to 225. And then similarly for the last one, right? So we have 112. Now this is B3H3, so we know these dimensions are going to be a little bit different, right? Because we're looking at that inner rectangle. So the inner one, if the wall thickness is 50 on both sides, then the base of that inner rectangle is 200. The height of it is going to be 350, right? So we have 450. The wall is 50 on this side, 50 on this side. So this is going to be 350. Area is easy, B3H3. And again, the centroidal distance, right, to the middle of this one, which is also going to be 225. So now, if you're going to calculate the total moment of inertia with respect to the x-axis, it would be Ix1 prime plus A1 D1 squared plus Ix2 prime plus A2 D2 squared. And now minus, right, because we're subtracting out that inner whole, plus A3 D3 squared. There you go. And again, the idea is that you'll be given this table, not expecting you to memorize all these moment of inertia formulas for simple shapes, but the idea is that you'll be able to apply them like we've done here.